This is webinar 2 of the Architectural Solar Association webinar series. If you missed the first one, they are posted on both the ASA YouTube channel as well as the NREL YouTube channel. You can find those and catch up. And I think you can definitely join this webinar today, number 2 of 5, without having to seen that first one. But yeah, definitely go back and watch it if you haven't. We're going to get into some cool, interesting details on a Boulder Commons project. And so this is going to be given to you by 3 different authors. Before I get into who those authors are, who we are, why we're telling you all this stuff, I'll do a little bit of housekeeping. There's 2 options for audio. You can listen through your computer, listen through your phone. There's a little black button on the bottom of the Zoom link down here. So if you have any problems getting your audio to work, you can definitely message the hosts. There's a host button on the bottom right. They can help you. We have both Lady Maya and folks from NREL here to help out. You can also, if you have any questions with it during the course of the webinar, we do encourage you to enter them into the chat before they leave your mind. There'll be time at the end to also ask questions, but there's a Q&A button down at the bottom as well. So Chris, if you can go ahead. Encourage you to ask questions. So who we are, this is a combination of both NREL, the National Renewable Energy Lab, and the Architectural Solar Association. This is work where we are combining efforts to try to basically develop architectural solar content and develop and deliver it through a number of different ways. We'll tell you as we go. So yeah, the National Renewable Energy Lab, which I'm talking to you from, NREL is a national lab. Our goal is to deploy and develop renewable energy technologies. Architectural Solar Association is a trade association with similar goals that are aligned, and so we're combining efforts here through a Department of Energy project. And so this is funded by the Solar Energy Technologies Office to develop an architectural solar education program for design and construction professionals like yourself. So with the goals of equipping building and solar industry professionals with with what it takes to deploy this type of technology. We're going to break down barriers, increase penetration, and definitely just promote architectural solar across the different areas. So this doesn't happen without a bunch of help. This is both funded by DOE and helped by a number of different organizations. You'll see on the bottom, they help us as the technical advisory group. There's also NRELians in that technical advisory group that help both develop and vet all the content you'll see today. So my name is Lance Wheeler. I'm a group manager at the National Renewable Energy Lab. I'll be acting sort of as your MC or your master of ceremonies today. Stan and Chris are your experts. Stan Pipkin is a design director at Architectural Solar Association, CEO of Lighthouse Solar. Chris Klinga is a technical director of ASA and principal at Solar Motive. You'll be hearing from all 3 of us today. And so before we kick off some of the actual content, I'm going to give you the learning objectives. We're basically going to give you a project, the Boulder Commons project, phase 1 project, and use it as a vehicle to deliver a number of different learning objectives. First, we'll start with, why is this thing architecturally significant? We'll gain an understanding of the design workflow through this project. We'll deliver on what the concept of solar area ratio is. We did cover that in the first webinar. And to gain an understanding of incremental cost, which is very important on the merits of architectural solar. And we'll do that through, again, the lens of the Boulder Commons project. So if you're not familiar with the Boulder Commons project, here's a quick overview. This is located in Boulder, Colorado. It's got a gross building area of about 95,000 square feet. It's a 4-story office building with 10 to 15 tenants. It was interconnected onto the grid in 2018, so it's been operational for nearly 7 years. It's got a gross solar area array of 45,000 square feet, module area of 29,000 square feet, and a PV system size of 571 kilowatts, and a total solar budget of about $2.3 million. So you can see through this series of photos that I showed you, there's 3 main types of arrays that you'll find on this building. There's roof, facade, and awning. And before we kick off some of the content in the webinar, what we'll do is do just sort of a knowledge check, if you will. And so you'll see on here 4 different questions. We're asking you, which surface has the best solar resource? And the options are the roof, facade, or awning. And you can see those different examples there, where the awning is the one running along the sidewalk there in the bottom of the building. The facade is facade, and the roof is the roof. Which surface will be most impacted by environmental factors? Which surface has the best kilowatt hour yield on a per kilowatt basis? And which surface has the lowest incremental cost? These are all concepts that will be covered throughout the seminar. What we want to do is a quick knowledge check to see where you guys are at and see if there's anything surprising about what we find. So I'll wait for Lady Maya to give me the word that we've got, enough responses here. And actually you can see them coming in real time here. So Stan, do you see anything interesting about these responses that you might not expect?
I think we should let them come in a little bit more. They are interesting. There's no doubt about it. But this is Chris. Sorry to interrupt, Stan.
Yeah, no, thanks, Lance, for the introduction. And yeah, I'm going through the responses now. It is interesting. And I think for those present, this was not meant to be a quiz to bring anybody on the spot, but it's we've found, in looking at this building and other buildings, we've always found some dimension that's kind of surprising and maybe counterintuitive. And so we will withhold going through the answers, the right answers. They'll come at the end of our webinar. We're really using these questions to try to frame our investigation of this project as a case study that it really illustrates kind of a larger set of questions for us that Lance mentioned. Our work to try to develop tools and best practices of how to get architecture solar out in the world begins with what's been tried and what kind of successes and what kind of merits those things have had in the world. So I will go from there so hold those questions in mind. We'll come back to them and we'll reveal the answers at the end. Make sure you stick around. Chris, do you want to go to the next slide and we'll jump in?
Yep, hold on one second.
Okay.
I'm gonna hit stop sharing on the
Okay.
on the poll there.
And while we're moving to the next slide, just another question or maybe statement for those that have joined us today. Our last webinar was well attended by a number of folks that were in the architectural solar industry in one way or another, and we had some that were in the design industry. And so for each of y'all, if wherever you fall in that spectrum, today's webinar, we're really I would ask you to listen from the lens of someone that may not be directly in the industry and sort of deeply involved in the practice of designing solar systems, on buildings, but really looking at it from the perspective of someone that is maybe tasked with incorporating solar, but ill-equipped with tools and/or support systems for their ability to do that. So we're thinking this is targeted largely to architectural firms or individual architects and designers who have aspiration but may not have the full support to be able to pull off a project like this. And that's partly why we chose this project. It's an accessible project. It was a market-based office building, and it was built in a largely from a market perspective, and the performance metrics were meant to solve very particular goals. So we'll get into that in a minute, but what was most striking for us to begin with is to really underscore what's really important about approaching a project like this. And so I think Chris and I in particular are often faced with the question, what about solar? And that comes oftentimes at the end of a project that's being constructed, and solar is an afterthought. And all the things that make solar a powerful design tool have been skipped or abrogated in a way where we just don't have the flexibility, and solar can't do everything when given limited chances. So we've developed what we think is a kind of best practice approach towards applying certain tools in a sequence. So beginning with, and this table is really meant to just outline the design phases on the left. And then the right four columns are what we think are the appropriate lenses and/or tools to apply during those phases. And so we'll get into a number of these in more detail throughout the presentation, but I think it's our focus today will be on the kind of looking at the early design, so feasibility, pre-design, schematic design as one set of tools, and then design development as a more refined set of tools. And so we see this as incremental. It's building on itself, and the tools are meant to be accessible, i.e., can be applied by someone that may not be an expert per se. So, Chris, you want to go to the next slide? One of the other aspects to this project that's actually quite interesting and was compelling is the stakeholders involved, and then the team that was assembled to pull off the project. So, as Lance intimated, this project is a commercial building, and the goal was to be net zero. And we'll talk a little bit about the financial structure in a minute, but it started with the building owner and developer having a clear goal, and then setting up a team to deliver on that goal. So the design team, the middle tranche here, what's notable for us is, and quite interesting, is the sustainability consultant and PV electrical engineer oftentimes are relegated to probably not as central a role. In this case, it was actually the same group, which, while we think it's an efficient manner to do that, in our analysis, it also sets up a potential challenge in that how that single group is operating kind of vis-a-vis the building owner's interest make it difficult at times when there's particular trade-offs. So we think that having a team comprised of kind of multiple entities is a really helpful way to keep the project on track and sort of test assumptions as you move through the design phase. In the implementation, likewise, the amount of coordination that is necessary to pull this project off is often, I would say, underestimated. And so they did have a strong team from the contractor, the electrician, the PV interests, a developer, and a coordination layer, and then a structural engineer as well. And so all to say, the solar system, applied to a building is not a plug and play system, in the sense that it's just something that can be specified by a solar EPC. It is a distinct and powerful system that needs to be coordinated with the rest of the building. And then finally, this was in the XL Energy territory in the city of Boulder, which is also quite a challenging jurisdictional market to work in. So they not only exceeded code, but I would say exceeded a lot of aspirations even in that city. The project goals, like I mentioned, they started with very compelling proposition. And what we find really remarkable, and part of the reason we chose this project, is they tied the financial performance of the building, i.e. from the developer's perspective, to the performance of the energy systems, both the targeted consumption. So it was a highly scrutinized and highly designed kind of demand level analysis of the building, and the building's ability to produce energy. And so that makes this project quite unique in that the solar system is not only central to in this case, the fabric of the building, but the energy and financial performance of the property, which is still quite rare in what we've seen. Just the metrics, and we'll get into this as we go through it a bit more. The EUI was below average, and that was one of the mechanisms that even allowed this to approach net zero. So, slide, Chris. So once they've determined a strong goal and have parameters to work within, the solar strategy was really, it was a holistic approach to looking at the building as a series of surfaces that have certain components and certain parameters to either maximize, optimize, or avoid. And so that process of looking at the massing of the building and determining without any preconceptions what that surface could do towards achieving their goal was really another unique aspect of the project. To get through that process, it's not simply one size fits all, but they took, again, a creative approach to each surface to understand not only how to optimize, but how to maximize the yield from that particular surface, and then looked for opportunities for the solar strategy to enhance the architectural program. So, and that's where we started to start to see the overlap between solar as an energy system and architectural solar as an integrated approach to the building's look, feel, and performance. One of the other things that we'll see, and that's unique to this project, is they maintained an off-the-shelf ethic. So the parts and pieces of the solar system were not highly customized, but they were outfitted to serve the purpose. This next slide is what we covered last webinar in more detail, but it's one of our framing techniques is to say the architectural solar is not a single thing. It's not an endpoint, but it's really a continuum. And so these are just our representations of different types of applications that fall in rough categories, each of which we believe require a enhanced level of integration and coordination. And we've grouped them in this manner just to have a kind of a quick index that starts to develop a language of how to approach this. So in this project, the three that we're looking at are building applied. That's the rooftop. Externally integrated, that's the awning. The cladding integrated is the facade. And note the color codes, those will show up later. Just trying to key into what those surfaces are. So this will be a little bit of some concepts just to register. This may be familiar to many on the call, but we've looked closely at how to approach a design process that moves from the highly generalized to the highly specific, but maintaining concepts that themselves can be somewhat flexible. So this is, for us, we've defined these as a way to keep clear of essentially falling into the weeds too quickly, which is oftentimes a problem with a challenge in projects. Solar area, and this is one of them that can either be the module area, so that's a very specific active energy producing area, or a gross area, which is serves kind of initial purposes when you're just looking at an entire surface. So consider this to be the entire roof square footage would be gross. Module would be calculating the actual area presenting to the sun. Power density, again, just the DC array capacity measured in square feet. And specific yield, we'll look at this, how we've come up with some shortcuts to find this, but it's essentially kilowatt hours per kilowatt, which is again a useful metric when you're doing early calculations. The last index is one that is less commonly used in the United States, but it's everywhere else in the world. It's probably more familiar. Again, we are looking to try to normalize a building's evaluation along square footage. So using square footage as the baseline. And EUI is something I think is quite common, where you're looking at building consumption per square foot. And we're placing EPI in kind of a companion role with EUI, and it's really the solar energy in kilowatt hours per square foot. We'll look at some different approaches to units. It's often you'll find it in kBTUs, but in our case, it's effectively the ratio that we're interested in, and you'll see EPI kind of through the rest of the presentation. And then finally, the EPI, there's different ways to calculate that. One of which is the specific yield times power density over 1,000. So key concepts, and we'll move on to, so the solar area ratio. Again, this is a concept we have tried to formalize in our first presentation. We introduced this. This is a bit of a recap of that. For those on the call that are familiar with the FAR, floor area ratio, it's a very powerful tool for developers when they're analyzing essentially the feasibility of a development on a given parcel of land. And we were looking for a concept that could achieve the same sort of quick evaluation, but it's powerful enough to be meaningful from a design perspective. And so SAR is that tool for us, and it's effectively the solar area over the conditioned floor area. So it directly implicates the massing of a building, the height, the width, the usable areas. And I would just put a pin in this. When we say solar area, that is the piece that will be variable over time as it gets refined in terms of what exactly are we meaning by that. The diagram to the right here is sort of indicating gross areas without any real indication of where the modules or where the active technologies are. And so we think this tool, even at its most at its highest level, is useful for a design team to establish a baseline or establish a goal in evaluating different design solutions, particularly at the massing level. Okay, Chris. And so when we apply that to this particular project, so the image on the right is just a abstraction. It's a 4-story building. And the areas, again, color coded. So the roof facade and the awning is actually projecting out from the building a bit, but it's at the lower level. And so we can establish pretty quickly this initial SAR as 0.48, and that's just doing the calculation. That gives us an idea, and we'll look at some ranges that can indicate the building's ability to achieve net zero. And it's based on a number of assumptions, but this can be a very very fast evaluation from a design team to see if their massing, which might be coming from developer goals, site constraints, height limitations, occupation, different architectural requirements, to see if that's going to fit in a program that meets certain energy goals. And below at the bottom are just different ways then to look at how the SAR is related to the relationship between EPI and the EUI, which is essentially the consumption, energy use intensity or utilization intensity. And so those calculations, again, start to give us a picture of what's the viability of a project to achieve certain high-level goals. Okay, Chris. And so quickly we can start to apply some very, very specific rules of thumb and some metrics that are generalized, but start to look at buildings. And this is on the column on the left. And this chart, by the way, is largely driven from the EIA kind of commercial building surveys. And so these EUIs can be applied to different types of occupations in buildings that then drive how we analyze, buildings' potential to meet a net zero capability. And net zero is not, for us, it's not assumed that it's the goal, but it's certainly a benchmark beyond which is kind of often difficult to justify. So it's an upper end oftentimes and can be used to measure one's ability to achieve that. So this as a metric and as a matrix of values, again, as a resource that we can see designers using, wouldn't have to go to the engineering, the MEP quite yet, to try to understand if their building is in the bubble, as it were. The note to the right here, when you start to look at SARs that are greater than 1, it's essentially indicating that the building itself as a set of surfaces may not be sufficient to achieve net zero, and we'd start looking at site applied or another strategy that's off the envelope of the building. Okay, Chris. So working our way kind of through this initial set of tools, I think these are quite familiar. Oftentimes, people understand that solar is respondent to orientation, location, and tilt. For example, I think what is less understood is the sensitivity to a surface's ability to produce energy is often it's less sensitive to the things that to orientation, for example. So when we start to look at a building's performance, we really do have to look at each surface and individually, and to understand if it's if it's viable and if it's makes sense from a overall performance or even a time-based performance. And so each of these we would consider to be high-level inputs that inform what a surface can do. But there's what we've found and what we recommend beginning with is a high-level approach that then slowly gets more refined, which may involve derating the system's performance based on a better understanding of the kind of limitations. So shade and snow, for example, often come at a second level evaluation that would derate the assumptions about what a system can perform. So the early assumptions may be slightly overstated, but we slowly through the process would refine those. Okay, Chris. So just as a primer on how we capture that performance methodology, we've used PV watts, and we know that there are many other tools out there, some of which are much more powerful, but oftentimes very difficult to manage quickly and at an early stage. So PV watts is it's been tested. The climate database is validated, and it can be used in a manner that supports these type of early design kind of evaluations. And it's also useful in that the derates can be applied selectively and throughout the design process that represent a more refined approach to how these surfaces perform. So we could go on to the next. So just for those that may not haven't seen PV watts, it is available. NREL hosts it, and when we talk about specific yield, this is sort of our approach to developing that very quickly. So the highlighted bubbles on the right-hand side, these are inputs, and you would essentially determine the location and then look at a certain surface that has a tilt and azimuth, and then we recommend using 1 kilowatt as the standard that gives you effectively the specific yield of that surface in that orientation and tilt. And we recommend assuming a certain level of system losses as a default, which just, again, builds in a bit of a conservative approach that could be refined over time. And that is our kind of stepwise methodology to try to build a case for solar and its application first on conservative estimates, and then slowly refine it to where it's more tied to the final assembly. Okay. Again, this is just a quick image. When we talk about snow and shade, it's certainly something you can't overestimate its importance, and sometimes it's not intuitive. And when we talk about architectural solar, slight changes in the building's massing create, sometimes unexpected effects. In this image of a small New England house where snow and shade coexist in unique ways, it is something that has to be modeled specifically. I'm showing here some images that are one approach that's very accessible is to produce a 3D model, run it through a solar simulator, and try to understand where those areas that are receiving more shade or more sun become evident. This can be used as a iterative design tool quite quickly. And I think the next slide. Yeah, so once this slide then is really a more of a composite approach to understanding how different applications start to work in their actual kind of field assembly. And so this we would consider another early design rule of thumb. And again, we've mapped out the architectural solar continuum with the assumed kind of yield from each of these applications. And so you can start to see the variation for each of them is determined by how much density they're actually involved. So inter-row spacing, if they're spacing for spandrels or mullions, or just wall area, for example, then your range you start to see a real range in the productive capacity of each surface. So Chris, I think next slide. This will be kind of a summation of this early design workflow. This is just one way to begin to calculate putting some of those tools to work. And again, this is applied to this project. So the inputs on the left, this is through your massing and schematic design, applying the rules of thumb, applying PV watts. And you can start to look at each surface, and the number on the right-hand side of this first block is that specific yield. And so that's starting to be quite informative as to the potential production of the building surfaces. And we haven't gone too far in the design process where we're looking at module technology or even the assembly, but it gives a designer a quick idea of whether this is going to be viable. And then from there, we would look at, to get back to ultimately to compare the EUI, we would like to look at how these numbers generate an EPI. And so the outputs from these early stages can generate for us a usable number that's comparable and can be calculated against the building's consumption. So I'm going to hand this off to Chris at this point. We're going to jump into the kind of next levels of the design process and sort of more refined set of tools.
Yeah, thanks so much, Stan. This is Chris Klinga. I'm the technical director of ASA, and I'm excited to speak with you all about how to take this, how the designers would take this project to the next step out of schematic design into a design development process, and looking at the massing of this project in particular. So Stan spoke of the D-rate tools. BIM Solar is a tool that's been developed in the EU. That's a great tool to use for that process. It's a free online tool that has SketchUp and Revit plugin capabilities. You can also use Rhino or with a Grasshopper plugin, or there's many different ways that architects analyze solar insolation. And so these images here are from BIM Solar, and they're analyzing the different surfaces, and they're clearly, it's a way to prioritize the surfaces. And the rooftop, as you can see, is the highest value real estate on the project. It has the highest performance and impact, but at the same time, access pathways are required, which reduce its overall power density. So other surfaces are good for other reasons, maybe power density being one of them. The southeastern facades on this project are the next best opportunity. They happen to be adjacent to a railway right away, which ensures solar access, whereas the west side of the project has development. So those developments have potential to shade the project. The image on the bottom here is actually the shading without the development, but it's just the shading of the mountains and the fact that those surfaces are facing a little bit northwest, and some of them are west facing. In Colorado, mountains play a role. Early morning performance is better than late in the day, mainly because of two factors. The horizon is higher from the mountains in Colorado, in Boulder specifically, in the Front Range, and then we also have super sunny mornings. So the southeast facades are great opportunities. The southern facade is interesting. On this particular project is limited in size, and whether or not it was better or it was limited in size, so it reduced the overall energy impact, and it kind of added complexity to the project. And so adding solar to that small area was a little bit of a challenge because it adds a lot of complexity to have an additional azimuth on the project. So they eliminated that from there, and instead focused on the architectural programming there to make sure that they were integrating the entry and all of the different things that needed to be prioritized over solar. And then on the west and northwestern facade, there's higher time of use rates. So those surfaces, while they're not necessarily as good from a performance perspective, they do have the opportunity to offset higher rates because there's higher billing rates at the end of the day when AC loads are higher. But that wasn't a driver for this project. They really wanted to just focus on total kilowatt hour production. We already talked about the less solar access, and so that's how we prioritize things. So as a next step, after we've got our surfaces prioritized, we would select a technology for those surfaces and use that technology to determine how much energy we can get on those surfaces. So in this particular project, they utilized a SunPower X21 345 commercial module, and that module had a module efficiency of about 21.2%. Keep in mind, don't get that confused with cell efficiency. The cell efficiency of these modules is higher than 21%. So you might hear modules touting high efficiencies in the mid-20s, but that's likely a cell efficiency. So it's important to just take the understand what the module efficiency is. And the module efficiency is directly related to the power per square foot of the module. So in this particular instance, 19.7 watts per square foot is equivalent to a 21.2% efficient module. And on the metric side of things, it's a lot easier to understand efficiency to power per meter squared, because on the metric side, it would be 212 watts per meter squared. So it's a quick conversion. And in this instance, we had 1,656 modules applied to the project at around 17.55 square feet, so totaling just over 29,000 square feet of module. And then the area, we went through and did some basic analysis of the area of the project based on satellite data, and determined that the gross area of those arrays is around 46,000 square feet. And so we achieved a gross power density of 12.4 watts per square foot on the project. And so another piece of this is how do you go about designing the rooftop? How do you choose a certain racking system? And this particular project utilized a dual tilt racking system that faced east and west. In this case, a little bit southeast and a little bit northwest. And there's a 10-degree tilt. And the reason to consider dual tilt is it maximizes gross kilowatt hour performance by fitting more power on the roof. And versus a single tilt system, which optimizes a kilowatt hour per kilowatt performance. So you can see here, the specific yield of a single tilt would be 1370, and the yield of a dual tilt would be 1249. But you're fitting more panels on the roof, so the overall you're seeing a higher energy gain. So in the end, the dual tilt is going to be a 31% higher cost in this instance, because there's 31% more modules, and then that's going to be for about 19% more energy. So and the challenges around dual tilt are, it has a lower rooftop performance due to snow buildup because of those that troughs where snow can build up and not melt away as easily. There's also lower bifacial performance when bifacial modules are utilized. And there's overall going to be a higher levelized cost of energy. But if your goal is kilowatt hour performance to get net zero, that's not the priority. And then also there's just also a limited supply chain. The last point is that O&M is a challenge, because you're packing the modules in so tight that access becomes quite a challenge. Whereas in a single tilt system, you have access via the rows, so maintaining modules is easier. But kilowatt hour performance was the focus here, so that's what they chose. And they got to 13.3 watts per square foot versus 10.2. So cladding versus awning. Well, on the cladding side of things, the big pros are you can match, you're broadening the energy curve of the building by going vertical. You're catching more sun in the morning or in the afternoon, depending on the surface it's on. And you're reducing your incremental cost because you're replacing a cladding material that would be there otherwise. In this particular project, they were able to leverage standard solar modules, which is very interesting because standard solar modules are very much commoditized, and their low cost per square foot is actually pretty intriguing when you're just comparing them to standard cladding systems. You're also going to get better power density on the cladding because of the density of the installation. But overall, you're going to have lower energy density because the orientation, and maintenance access is an issue, something to consider. And an overall install cost is going to be up because you're going to have lifts to get up there. On the awning side of things, you're going to have higher performance, assuming the shading from the building doesn't affect it too much. And you're also going to provide shade for those windows below. And in this instance, they had an area of that lower awning portion where there were vents for all of the heat pumps for the project. So the awning coexisted with those heat pumps, that they couldn't clad that area because it was all vented. So in this instance, it spanned the windows and the vents. But overall, it's going to have a lower power density because you're not covering as much of the surface. There is self-shading to consider with the awning too. If you did multiple rows of awnings, you have to spread them out so they don't shade one another. And you wouldn't want to do the awning above the cladding per se, because you would shade the cladding. So in this instance, the awning was on the ground floor, and that made the most sense. And overall, it's just going to be a higher cost for the awning because of that steel structure. And in our analysis, we're not considering that. We're adding that as part of the incremental cost, which impacts things. So on a power, here are the metrics that are really exciting. So on a power per square foot basis, when we consider that whole wall area of the awning, it's at 7.6 watts per square foot, whereas the cladding area is 12.1. And the specific yield of the awning is better at 1192 compared to the cladding at just over 1,000. But in the end, the cladding wins out on the gross area of this particular project. It hits 12.1 kilowatt hours per square foot versus the awning, which is 9.1, because it has that lower energy density, that lower power density. It relates to a lower EPI figure. And so in the end, the best solution was implementing awnings on the lowest level and claddings on the upper levels. And in terms of maximizing kilowatt hours, this project also utilized a high efficiency solar module. Those sun power modules in 2017 were 345 watts. That was very high efficiency for that time. This day and age, that same sun power module is marketed as a 370 watt module. That being said, SunPower did just go bankrupt, and unfortunately, those modules are no longer available. But what's interesting here is the increase, right? Between 2017 and 2024, that was about a 1% increase per year in efficiency. And yeah, so this project would even be more efficient if it was utilizing modules today. And SolarEdge was utilized to have module level power electronics. So each one of those solar panels is monitored individually on this project. And this is a great thing from a power production perspective, assuming that those added points of failure aren't an issue. This day and age, you need to, all of these systems need to have rapid shutdown compliance. SolarEdge is a path to that, and it does so while adding optimization, which helps shade performance. And in the end, the biggest maximizing kilowatt hour features here are, on the roof, the reduced space between the modules, going dual tilt versus single tilt, and then ultimately just implementing the cladding and the awning just absolutely increase the kilowatt hour performance of the building. And here we go through a quick PV watts analysis, that the same analysis that Stan outlined previously. PV watts, you need tilt and azimuth as the main inputs beyond the location. And here you can see all of the figures for each of the 2440 and 2490 are the two addresses on the project. And so this is all tabulated here. I won't go through all the data, but you can see at a high level, the externally integrated awning is performing the best out of everything. On 2490, it's at 1309. And the rooftop is 1246 on 2490 and 1249 on 2440. So pretty darn similar to the awning in the end. And then the cladding system is where the cladding makes up is that the environmental factors actually don't impact that as much. So there's no snow loss on the cladding system because it doesn't build up. And then in this instance, there's no shading from the right of way. So those 983 and 1019 figures on the cladding system actually don't get reduced in our next step. And so here we're applying a D rate based on an analysis we did in BIM Solar of the building. And for the rooftop system, we utilized NREL's snow modeling tool to determine that the snow impact would be about 8% on this project. So we derated that, and then on the awning, there's also some impact on the snow, but not as much. But the impact on the awning is more from the fact that in the afternoon, the building itself shades that awning. And then there's no shading impact on the cladding itself because the insulation figures take into account the self-shading of the building. And so in the end, those cladding numbers actually level out a little bit with the other numbers. And on 2490, the cladding system is at 1,019 kilowatt hours per kilowatt per year, and that's approaching the rooftop array. So this text is a little bit small. I apologize for that, but the idea here is that it provides you a sense of like the next step in the workflow. Stan showed you that first step, which was the schematic design workflow up top. We didn't apply any D rates to that step, so the numbers were a little bit high. But then the idea is that when you go down into this next step, rather than using rules of thumb, we've actually selected the technology, we've done the layouts, and so we've put modules on different surfaces, and we've multiplied the module power by the module quantity to get the overall array power. And then we can multiply that by the D-rated specific yield to get the actual performance. And that D-rated specific yield, the D-rate analysis is done in an outside tool where we understand, the focus is to determine what the overall solar access impact is. And so in the case of the rooftop, it was 92%. So it was that 8% hit from the snow. On the awning, it was an 8% hit from just the building shade. And on the cladding, there was no hit. So then that gets us to the numbers. And then ultimately, the numbers that you get out of an analysis like that can be your rules of thumb for future projects. So the power density figures, in this instance, it was 19.7 watts per square foot because all the modules are the same. And then we had a fill factor on each of the surfaces that determined what the gross power density was. So these gross power density figures in the lower right are great metrics to use on future projects for roof mount, awnings, or cladding systems. And in this instance, it's just another look at the building applied PV rooftop and a view of it and the yields. So the two figures that are the big wins on this system is the 15.3 is really high. It's great yield on a per square foot basis of kilowatt hours. And then also just the overall power impact that the rooftop contributed 373 kilowatts to the project. The rooftop racking system was an Orion racking solution back in 2017. That company is no longer offering that solution, but there's plenty of other solutions on the market. Today, most of the newer solutions on the market today have access pathways, which is great. This older system didn't, but it maximized kilowatt hours. And the added dead load on this project was around 4 PSF. It was designed for 150-mile-an-hour wind and exposure C, and it had a roof snow load of 30 PSF. The cladding integrated system was around 160 kilowatts over both buildings. It had an average performance of around 1,001 kilowatt hours per kilowatt per year, and then EPI figure of 12.1. And then the externally integrated figures, they had the best specific yield of any of the surfaces at 1192 and around 37 kilowatts, and both 9.1 watts per square foot as well as kilowatt hours per square foot. And the facade and the awning systems utilized a Unirac sun frame system, which is a shared rail system. This product is also discontinued at this point, but there's other products on the market today that offer a similar solution. The idea here is that that racking system closed off the gaps in between the modules, created a nice architectural finish from the front, full closure. And then you can see they also implemented expanded sheet metal on the sides to keep birds out. And overall, there's hardly any dead load on the wall, only about 3 PSF. And it was tech screwed into a Z-girt system. And then thankfully, Boulder Commons, one of its tenants is Rocky Mountain Institute, and they did a great case study on this project. And we've got some great cost data from that case study, but it's linked here, and we'll provide in the PowerPoint. And the system cost was estimated at 2.3 million. And within the Boulder Commons study, they also call out that the cladding cost of the project was around $84. Sorry, the cladding system, the PV cladding system was $84 a square foot, and then the avoided cost was $42. That's because the metal cladding costs $42, and so we avoided $42, and so the incremental cost of the cladding ended up being right around $42, which is super interesting. ASA took this cost data and tried to discern like what the other portions of the system would cost based on some industry knowledge that we have. So take it all with a grain of salt, but we believe it's a sound approach. The darker fields are the fields that the direct inputs that we got from the study. And the overall concept here is that there's baseline cost, avoided cost, and the incremental cost. And so baseline plus avoided, or sorry, it should say minus. I don't know why it says plus. It should say baseline minus avoided equals incremental. And in this instance, the rooftop had a baseline cost of $70 a square foot. We didn't avoid anything, so the incremental cost was 70. And on the awning side, it was $148 a square foot. And that's mainly due to the cost of the added steel. And what ASA did is we looked at the roof. We looked at the cladding cost, which was determined from the Boulder Commons study, and then discerned that there was $3.93 per watt left over to allocate. And then we said, okay, well, what is about the cost of a rooftop system, and what is the cost of this added steel? And so we did some estimates on the cost of added steel for that awning structure and came up with a cost per watt of the awning of $7.55 a watt. There was quite a bit of steel there for the overall length of the awning, for how many solar panels it supported. And then we took that $7.55 and backed out what would the resulting cost on the rooftop would be, and determined that it was right around $3.57, and $3.57 per watt at this time in 2017 was about what would make sense for a system install cost. So take these numbers with a grain of salt, but the ultimate goal here was trying to land on what the overall incremental cost of the system was, and that's in that lower right of $3.43. So the system started at $4.03 from an upfront cost perspective when you take into account the $2.3 million. But then when we subtract the cost of cladding that we're replacing, the effective incremental cost of the system was $3.43. And so what's really interesting to me here is that the rooftop system is $3.57, and the system as a whole, when we take off that cladding, is still below the incremental cost of the rooftop. So $3.43 is better than $3.57. So some projects may choose to just do rooftop, but in this instance, the architectural integration actually reduced the overall cost of the installation on a per watt basis, as well as a per square foot basis. 67 cents or $67 a square foot for the total system, compared to the roof, which was done at 70. And this slide just articulates that value of the cladding and really how it's pushing the envelope forward. Put things into perspective. a 50 cent per watt module at 20 watts per square foot is going to have a cost per square foot, material cost of $10 per square foot. There's plenty of cladding materials today that are more expensive than $10 per square foot from a material cost perspective. And, you know, these commodity modules are, and 50 cents is a very high number, mind you. Today, you can purchase modules in the 20 cent or less range. And if you would, that would mean that they're in the $5 per square foot range at 25 cents, which is super interesting from a building material perspective. And then overall, if we looked at $3 to $4 per watt installation costs at 20 watts per square foot, that would equate to a $60 to $80 per square foot total cost. So that's installed. And that's a typical range that we see for commercial systems. And so in the end, there's plenty of facades being built today that are more expensive than $100 a square foot. And solar systems are getting done at $60 to $80 per square foot. So this is something to pay attention to. And just to sum up the incremental cost thing again, where all these figures should be minus, but baseline minus avoided is equal to incremental. So this just sums up what we spoke to previously. And then overall, another interesting thing is what was the energy impact of each of the surfaces? The rooftop impacted the overall project by 68%, but it had the highest incremental, or it had a higher incremental cost than the project as a whole. The awning was at 77% energy impact, and then the cladding 25%. The cladding at $42 per square foot and a quarter of the project is super exciting. So overall, all this data has been pulled from the Boulder Commons RMI report, and we look forward to distributing it to you all at the conclusion of this. And at this point, let's just circle back to that intro set of questions. So we asked which surface has the best solar resource, and I think most folks got that right. It's the roof. And which surface would be most impacted by environmental factors? In this instance, it's the roof, but most folks, plenty of folks got that incorrect. They said the facade. And that the reason it is the roof, it's because snow impacts the roof by 9% in this, or 8% in this specific system. And then in terms of kilowatt hour yield on a per kilowatt basis, the awning performs best. And then in terms of an incremental cost, the facade has the best incremental cost because it's the only portion of the system that actually replaces a building material. And at this point, we'll just take questions. We've only got a couple minutes left, but we're happy to extend it, assuming the webinar won't cut us off. And Lance, I'll let you drive the conversation.
Sure. Yeah, we got a couple good questions in the chat here. The first one comes from Adrian Gallo. He's asking about HVAC systems and how they often occupy a roof surface area. So how do you go about designing a building when you know you need area for the HVAC systems, and that maybe you can even talk about what they did for the Boulder Commons.
Yeah, so that's a great point. At Boulder Commons, they integrated the HVAC into that ground floor. I believe they're maybe even in the parking garage below, and then they vent out below that awning. And so that was one strategy that they did. So you can see that in this picture, on 2440, there's a large area with vents in the lower left where some of the upper portion of the awnings removed. They're vented there. Typically, we see them on the roof. This system saw an energy density of around 13 or 14 watts per square foot, I believe, if I recall correctly. But typically, we actually, because of the rooftop units, we'll see systems in the 8 to 10 watts per square foot because of how much area that those rooftop units take up. So if you can get them off the building, great. But at the same time, I think being on the building, those units operate the most efficiently. So it's a trade-off. If you bury them inside the core of the building, you need to figure out how to get air to them.
I would just add to that. It's a very I would say it's a difficult thing to solve if the MEP design of the building has gone kind of has progressed without any indication of the solar being part of the project. There are opportunities to work with the mechanical engineers to massage the location of equipment on the roof, if given the chance. And I think what we've encountered oftentimes is it's just there's an efficient way to place those on the roof by, to solve other parameters, and solar is often responding to that. When we've had the chance to engage MEPs on that, it's a very straightforward conversation about just massaging the location or density of HVAC units. And this is, I'm thinking, for example, multifamily is when it's particularly challenging, just the design of most of those rooftops. But yeah, I think it just speaks to trying to engage the solar discussion as early as possible. And part of our approach is to say it can be a low-calorie approach. It doesn't have to be a full commitment and derail the team, but it gives people some working parameters that gives solar a chance to sort of get into the deeper levels of integration.
I would also like to point out that a lot of the times just moving the rooftop units to a certain portion of the project or co-locating them with fire access pathways can really help. Usually those units are a biggest impact if they're on the south side of the building. They will shade a large chunk of the roof. So putting them on the north side of the building solves a lot of those problems.
So I've got, I guess we have 5 questions here, and I actually need to jump off, but maybe I'll ask one here and then I will jump off. But the question, I like this one. This was, of the thousands of options for PV panels, why did you choose the ones that you did? And I think there's interesting things that you can probably expand on too, about like when you lose access to panels because, a company goes bankrupt. I guess any sort of insights you have on choice of panels, or what you do when you can't buy these panels anymore.
Yeah, absolutely. And I can kind of take over, Lance, if you need to go, assuming we can keep running long if need be. So as far as panel selection, it's a big topic, especially given that for a long time, I think that what you do is the number one approach from my perspective is understanding where the supply chain is the most robust, choosing suppliers that are tried and true, have been in the industry for a long time. Ironically, SunPower was one of those suppliers, and they recently went bankrupt. 10 years ago, they would probably be the top pick of many installers, and they were in this instance. So I think that they were chosen because they were thought of as a very strong player. And in this instance, SunPower also had a premium product with higher efficiency cell technologies, and that was cutting edge at the time. And the folks at Integral Group, and just to be clear, I did not design this building, and I'm just analyzing it, neither did Stan. So Integral Group are the PV designers of record, and I believe they go by the name Introba now, but they chose the SunPower panel mainly because of just the kilowatt hour performance.
Yeah, I would just add, I think it's a great question, and it's actually something that the entire solar industry is grappling with, not just in terms of integrated solutions, but any type of long-term. I mean, it's a robust material, so it's designed to be in the environment for a long time. The utility scale industry is dealing with this with regards to hail events in particular. And so looking at form factors and electrical performances for panel replacements as wattages have been increasing steadily. It's just a consideration that has to be made, and a strategy has to be put in place to either accommodate different form factors later. We've had a lot of clients that will buy panel reserves and just keep them on hand out of the sun, and those can handle sort of minor interruptions. But if you have a system like this where it's a framed mounting system, if the system itself can be designed in a way to accommodate changes over time without compromising the architectural intent, that's another strategy, is sort of build in some form of flexibility. The more integrated the solution is, I think the more challenging the solution to that question becomes. And it's less about, finding a panel to substitute, and it's more about going straight to the material assembly. But yeah, I think that's the industry has been growing, and Chris's indication of just the wattage going up, that's within the same form factor, but the panel industry is actually diversified quite a bit on different cell. So the individual cells have changed size, which has had pretty enormous impacts across the board on variation of form factors on the sizes of panels, the physical sizes. So it is something to consider very carefully. I don't think we have a easy answer for it, honestly.
Yeah, I know I'm noticing here that Oleg had a question. Is also SunPower. He noted SunPower filed for bankruptcy in August of this year. What other PV manufacturers would you recommend to specify? I'm sure if I specify one, I'll quickly put my foot in my mouth. So by the next webinar, so I'm going to avoid specifying a particular manufacturer, but I'll just say like the domestic manufacturers, there's a bunch that are that have popped up, and just them being in your backyard, I think that is a great thing to focus on. And in addition to that, there's also, if you're looking for more integrated products, you likely will have to look to the EU. Most of the manufacturers there have far more robust BIPV specific offerings. And if I was going to bestow one tidbit of wisdom, it seems like the industry is coalescing around a specific width dimension of around 1143 millimeters. And that is, you're seeing these certain widths be very consistent manufacturer to manufacturer. So the length of the module tends to change a bit manufacturer to manufacturer, more so than the width, but trying to standardize your designs around the most standard widths would prove to be very beneficial, because it will create a wider supply chain of opportunities should you need to replace modules down the road.
I think Lady Maya was indicating we need to wrap up.
All right. Yeah, it sounds like we do. And we'd like to just thank everybody for their time today. And here are the references, just so you've got that information. We'll distribute the slides, and before doing so, I'm gonna fix the avoided cost calculation error, which will have a minus in it.
And there was another question about sharing the recording, which we can also do that as well.
Absolutely. And we will share the recording, and it will be published. This whole thing will be published on YouTube, so it'll be readily available. And feel free to email us more questions. One thing we failed to do was add our emails here. Stan and I can both be reached at Chris, that's CHRIS, at arcsolar.org. That's ARCHSOLAR.org. Stan is, I believe, STAN at arcsolar.org as well. So thank you so much for everyone's time. We look forward to seeing you on the next webinar.
Thanks for everyone's attention.